All right, here we go. Here's your homework. All right, today we're going to be doing three shapes: parallelograms, triangles, rhombus or rhombi, and we're going to get a formula for the area of each. You should already know the parallelograms, triangles, but you should not be familiar with the rhombus one. Okay. Well, we're going to immediately jump right in with a proof of why the area of a parallelogram is equal to base times height. You've probably known that since about sixth grade. Let's prove it now. All right, so what am I going to do? I'm immediately going to make two triangles. So I'm going to drop a perpendicular from P and a perpendicular straight down from Q. I'm going to have to extend SR a little bit to make those intersect. And I made two cute little triangles right there. All right, well, let's see. Let's see if the black portion there is a parallelogram. We know that opposite sides are congruent. So that would mean, let's see, I know that PV and QT would be congruent. Why? Because well, if PQ and SR are parallel, then any perpendicular drop down will be equal. I could also say that PQTV is a rectangle. Opposite sides congruent, four right angles, therefore it's a rectangle. That's going to be helpful at the end of the proof. And then I could probably show that the two triangles are congruent. Let's see, if PV and QT are congruent, well, so is PS and QR. So that would give me a hypotenuse leg. So therefore, the two tiny little triangles are congruent. And now I'm going to get to the heart of the proof. Now, you might get lost on the letters, so pause it, rewind it, listen to it again. So here's my first statement. I'm going to say that PQRS, so PQRS is the parallelogram, and that would be equal to, I'm going to cut that parallelogram up into tiny parts, PQRV. So that's, well, we don't have trapezoid yet, but that would be a trapezoid plus PSV. So that would make the entire parallelogram. So that was what, postulate 19 that said you can take the shape, break it up into individual non-overlapping parts, and then add them together. Okay, I'm going to make another statement like that. It's going to look similar, the letters, but it's different. So what's PQTV? PQTV is a rectangle, and that rectangle will be made up the little triangle on the right, that's QTR, and the other trapezoid PQRV. Okay, now why in the world am I saying that? Well, we're going to do a little bit of substitution. So here's the statement that PQTV, which we already said was a rectangle. Well, that's equal to base times height. And then I'm going to do a bunch of substitution. Now, I didn't want to have a second page and draw this, so I'm just going to talk you through the substitution. Here's the substitution. These two right here, it's stated right here, are the same value. So I'm going to substitute. Now I'm going to clear those out. I'm going to substitute for QTR. I'm going to substitute PSV. Why aren't you drawing? I'm going to try that again. So for that, I'm going to substitute PSV. And I can because of that previous statement that says that the two little triangles are congruent. Okay. If that's true, then that means these two are equal to each other, right? Because it literally says the same thing now. Right here and right here, it says exactly the same thing. So therefore, I could, let me do this in red. I could say that these two in the rectangle are equal to each other by a second substitution. And since this says that PQTV is equal to base times height, then so does PQRS, right? And that's the end of the proof right there. I just didn't want to have a whole new sheet of paper just to have one extra statement. Okay, so I just proved that the area of a parallelogram is base times height. So that is your next theorem. Theorem 11.2, which states the following, that the area of a parallelogram equals the product of the base times the height to that base. So there's two letters right there, B and H. B is the base. Remember, the base could be any side of the parallelogram, but the distance between the base and the opposite side is called the height. Yes, we generally use the bottom as the base, but it could be the left or the right side. And I'm going to draw this. Is going to be ugly, but I'll try. If we make this side the base right here, maybe I'll do that in blue. If we make this side the base right here, so this side right there, that's the base, then I need to draw a perpendicular line from there to the opposite side. Notice this is one of those ones where we would have to extend the side right here. I can't draw a dotted line using this program right here. So sometimes the height would be, and they wouldn't draw the blue line right there. If they were to do that, they would draw the blue line from the vertex straight. Why aren't you drawing? They would draw it from the vertex straight down. So if that was the height, it would look like that. Connect the red line to the blue line. Okay. Let me erase all that. All right, make sure you have this copied down. That's our first theorem. And, well, if you were in 8th grade, it would look like this. They'd give you a parallelogram, they give you the base and the height, you multiply the two together, and you get 10, and you got to put the square units, so 10 square feet, and it would be nice and easy. But we're not in 8th grade, we're in 10th grade. So you're going to get a 10th grade problem. So it's going to be much more challenging. So they're going to throw special right triangles or trig at you immediately. So just recall, just a reminder, we have two special right triangles, 45, 45, 90, and 30, 60, 90s with the side links as listed right here. So have this handy when we do the next couple problems and when you do homework. Not all of the homework problems will require you to do special right triangles, but some of them will. Okay, so here's our example. Calculate the area. It should say of the parallelogram. So calculate the area of the parallelogram. Well, we need the base and multiply it by the height. The base is 10 and the height isn't listed. But I do have an angle there. And if you notice that angle right there is 45 degrees. So it's a 45. This triangle right here is a 45, 45, 90 triangle. And remember, if it's a 45, 45, 90, well, let's see, we need H, and H on our picture would be this value right here, which is not listed. But we got this 8, and this 8 would correspond with a root 2. So that's what I'm going to do. Now I'm going to use an H instead of an A. So 8 is equal to a root 2, except I'm going to make it an H root 2. It's the same thing, just different variable. And just simply solve for H. So remember the problems that look like this, we don't square both sides because you'd get H squared. We're going to divide by the square root of 2. And if you divide both sides by the square root of 2, the square root of 2's would cancel, and you'll be left with 8 divided by the square root of 2, which unfortunately you can't have. You can't have a square root in the bottom, so we multiply top and bottom by the square root of 2 to rationalize it. So we would get 8 root 2 over the square root of 4. Square root of 4 is 2. So I did a couple steps right there. I multiplied the top with the top, the bottom with the bottom. The bottom would give me the square root of 4, but the square root of 4 is 2. And lastly, 8 divided by 2 is 4. So we get 4 root 2. So I'm going to take that 4 root 2 and toss it into my H right there. Well, that's pretty easy math. 10 times 4 is 40. So we would get 40 root 2. And we got to put the units. There are no units listed, so we just put square units. Let me get rid of all that mess there. There you go. Well, that is not a simple one. That's not an 8th grade problem. That is a 10th grade problem. Okay. If you were in class, you know our class, I'd have to give the speech about why is it so difficult? Because, you're not in 8th grade, world is difficult, real life is hard. You've heard my speeches before, but just be ready. These are not very, very easy problems, most of them. All right, so I'm going to do one example like that, and we're going to move on to the next shape. So it's still pretty straightforward for parallelogram. It's just base times height, but you're going to have to find out what the base is. You're going to have to find out the height using either trig or special right triangles. Remember, trig is the SOHCAHTOA using your calculator. All right, so let's see what we got here. We got a triangle, and I'm going to finally prove that the area of a triangle is 1/2 base times height. Notice it doesn't say that. It says 1/2 YZ. Well, YC is the bottom of the triangle, and H is the height. Remember, the height is defined as the perpendicular distance between a vertex and the opposite side. So yes, this actually says base times height, just in the form of what the triangle you're given. All right, let's prove this one. We're going to make another shape here. So we're not going to make another triangle. I'm going to make a parallelogram. So here's how I'm going to make it. I'm going to extend a line that starts at X and is parallel to YZ. So I'm going to make that one right there. And then I'm going to do the same thing through Z. I'm going to extend a line and make it parallel to YX or XY. And it's going to intersect that other red dotted line. At some point, I'm going to call that point W. Now, the question is, did I make a parallelogram? Well, the literal definition of parallelogram is that opposite sides are parallel. And yes, I did that. So you have a parallelogram if you combine the red with the black. So the outer portion right there is, in fact, a parallelogram because of the definition. Opposite sides are parallel. All right, now what am I going to do? Well, the parallelogram itself, right, has some congruent parts to it. Let's see. Opposite sides are congruent. So XW and YZ are opposite. They would be congruent. XY and YWZ are opposite each other. So they would be congruent. And I'm just going to pick an opposite angles, angle Y and angle W. I could also do this proof as well, saying another piece I'll tell you here in a second. So the properties of parallelograms, opposite sides congruent, opposite angles congruent, consecutive angles are supplementary. Those were their properties, remember? There's a few more I left off. Okay, now why did I do that? Because I'm going to show you that the two triangles are congruent. So let me put some tick marks, congruent, congruent, and what do we say which angle? Oh yeah, Y and W are congruent. And look, I got an SAS. So the black triangle and the red triangle are congruent because of SAS. I could have also said XZ is congruent by reflexive property. I could have gone that route as well too. SAS is just as good. Okay, so I proved that the two triangles are congruent. So now I'm going to pull it all together. So the big shape itself is a parallelogram, and that parallelogram is X, W, Z, Y. And that would be equal to the area of the two triangles, the black one and the red one added together. That's postulate 19. Why did I go that route? Because I know the area of a parallelogram. It's base times height. I know that if the two triangles are congruent, I can substitute one for the other or double one of them. So that's what I just did right there. All I did was, let me mark this one up. All I did was take, since I have this statement right here that the two triangles congruent, I can double this one and it would be the same as adding the two together. So that's what I did right here. Just double one of those would be exactly the same statement as this part, right? Why do you stop drawing? The same thing as this statement right here. All right, back to our thing. So let's see. Area of X, W, Z, Y is a parallelogram, and that's base times height. So I can write that base times height. Well, what's the base? The base is YZ, and the height is that H right there of the parallelogram. All I got to do now is divide both sides by 2, and I get to this last statement. Yes, I wrote it backwards, but you get the idea. I'm just dividing both sides by 2. And so on the right side, let's see, the 2 would just disappear, and on the left side, it would turn into a half. And there you go, proved. This is once again why, I mean, you learned the area of a triangle way back in 5th grade, and they certainly don't, you can't prove that in 5th grade, but you can in 10th grade. All right, so let's write that one down. That's the second to the last one. Area of a triangle is equal 1/2 base times height. So the area of a triangle equals half the product of the base times the height to that base. Lastly, I'll add most people, now this is the formula in every single math book that I've ever encountered, but I'll say most students and most teachers, when they actually do the calculation, like you're grabbing your calculator, you're doing your calculation, they generally do base times height divided by 2. So I would absolutely write both of those down. The second one is a bit more easy to use with a calculator. Okay, if you need the definition of base, it's any side of the triangle, and the height is the perpendicular distance between the vertex and the opposite side. And if the opposite side is the base, that's the one we want. Okay. I left this in here. This is actually a note to my other class, who I have a student who needs a little bit, he's actually in 8th grade. They're taking geometry, and every time I would say, you're not in 8th grade, Nixon would say, yes, I'm in 8th grade. And I would, explain to Nixon what I mean there. So these are going to be challenging because you're not in 8th grade. So check it out. What's the area of this triangle? Notice what we're missing. We're missing a height here. So we got to actually, well, I mean, we could plug in the base. I mean, if the bottom is the base, then the base is 6, and I still need the height. Well, if you remember, take a look at the triangle. It is isosceles, and we have that one thing that says that if you have an isosceles triangle and you draw an angle bisector from that vertex there at the top, that it turns into a perpendicular bisector. Therefore, that one of those triangles there, the left one or the right one, has a length of 3, and well, the other one is 3 as well. So it breaks that bottom into half. Now I got a right triangle. I got two of the sides. Remember, I want that dotted line to be the height, so I could use the Pythagorean theorem. So let's see, 8 is the hypotenuse, so that would be your c squared. So 8 squared is equal to 3 squared plus x squared, ab squared, whatever you want to call it. I'm going to call it h squared. Just simply solve that. Let's see, 8 squared is 64, 3 squared is 9, subtract 9, and that would be 55. And it's not a friendly answer. Square root of 55. Right, we're expecting a nice friendly answer, but you're in 10th grade. So I take this, that is my h, I toss it into that right there. 6 divided by 2 is 3, so it's 3 times root 55, and put a square units on it, and we're done. Okay. One more challenging one. So I remember I said we would also use trig or special right triangles, remember? All right, so let's see what happens here. I got an equilateral triangle here. All the sides are the same. Same technique as we used the previous one. So equilateral triangle, drop a height down. It still cuts the bottom in half. Once again, I can use Pythagorean theorem, right? So if the base is 6, I just need to figure out what is the h. Now on an equilateral triangle, something special happens. On an equilateral triangle, right? I know it's a 30, 60, 90 triangle. Why do I know it's 30, 60, 90? Well, if it's an equilateral triangle, then all the angles are 60 degrees. And if I just cut the top one in half, well, then the top one is 30 degrees. So it's a 30, 60, 90 triangle. I think I have that in my notation. Let's see. Sure do. All right. So let's see. We're given 2a, right? So 2a is equal to 6, right? So if h is equal to a root 3, well, that's pretty easy because I know that 2a is equal to 6. Therefore, a is equal to 3. Do you see where I'm getting that from? Right? So let me annotate it for you. So 2a is equal to the 6. So 2a is equal to 6, and that means a is equal to 3, if I solve that. And if a is equal to 3, well, then anywhere I see an a, I write a 3. And guess what? Our formula says here for h is a root 3, so therefore it's 3 root 3. So if h is 3 root 3, I also could use Pythagorean theorem as well, too. We'll still get 3 root 3, right? Wait, 27, 9 times 3. The square root of 9 is 3. So 27 can be written as 9 times 3. Take out the square root of 9, which is 3, and you're left with 3 root 3. So either method worked. Special right triangle, Pythagorean theorem. So I take that value, 3 root 3, toss it into my h. 6 divided by 2 is 3, or let's see, 18. 6 times 3 is 18. 18 divided by 2 is 9. So we get 9 root 3 square units. All right. So a little challenging, especially since it's right triangles. We got one shape left, right? And this will be the first new formula that you'll encounter in this chapter. All right, so it's the formula for area of a rhombus. So the area of a rhombus is, well, apparently it's equal to 1/2 the two diagonals multiplied together, d for diagonals. Well, we got to prove that one. So this one's actually a pretty simple proof. All right, so what am I going to do? First thing I'm going to do is simply claim that the big triangles, I'll write them in green here. The two big triangles. So this one right here and this one right here are congruent. Why are they congruent? Now let me clear all that mess out. Well, let's see. It's a rhombus, so all the sides are equal to each other. So that means, let's say this side is congruent to this side. Well, this side is the same as all the four sides are the same. And then we got a reflexive property in the middle, so because of SSS, right? All right. Great. Those two triangles are congruent. Now what? Well, if they're triangles, from the previous theorem, I have the formula for the area. So let's see, the area of a triangle is 1/2 base times height. So let's see that math. So for just one of the triangles, I'm doing, let's see, triangle ADC. So that's the big triangle here on the left, this one right here. So if I consider that D1 is the base, that's the blue one, then the height would be, well, it's not D2 because D2 goes the entire length. So I need to take half of D2. So the formula says the area of a triangle is 1/2 times the base times this is the height, 1/2 of D2. Okay. Cool. Okay, if that's the area of that, and the previous statement says that these two triangles are equal, so the whole darn thing, which is the rhombus, would be equal to the, well, let's see, if I pull this half out, right? A half times a half is a quarter, right? And then the last statement I'm going to make is that the area of the whole darn thing is the two triangles added together. In green here, it says the two triangles are congruent. So the triangle of ADC plus the triangle of ABC will be the whole darn thing. Since they are congruent, I can say two of ADCs, right? I could literally say two of ADCs will be equal to it. And I'll do this in red now. Now, if this is ADC, then if I do two of them, I got the whole darn thing. And what's 2 times a fourth? 2 over 4, which is a half. And we're done. We've actually proved it. All right. So that is the proof of why the area of a rhombus is a half times the two diagonals multiplied together. Now, you've never seen that one before. So we definitely need to write this one down. And as always, most people, when they're doing a calculator, it would be the two diagonals multiplied together divided by 2. It actually shortens the number of keystrokes by 1 keystroke. Mathematicians love that. Okay, if you need a definition of diagonal, it's the distance from one vertex to the opposite vertex. Area of a rhombus is equal to base times height as well, because it's a parallelogram. You may use either one, but guess what? They're going to give you the diagonals, so you probably won't be able to use base times height. But you could, if they just happen to give you the base and the height, you could use that formula as well, because remember, a rhombus is also a parallelogram. All right, so that's going to do it for today. I'll go to the homework. So this is roughly what your homework looks like here. Notice I don't have a base and height for, I got a base for one of those rhombus, but I don't have a height. So remember, the second thing I would just point out for rhombus, which I should have pointed out in the instruction, is that the diagonals of a rhombus always intersect at right angles, and they bisect each other as well too. So look at number 7. Notice both sides are 2, and the other diagonal, both sides are 5. So the diagonals bisect each other and they form right angles, and that will be helpful. Either Pythagorean theorem or special right triangles. Notice number 5 there, that's a special right triangle. 4 will be a special right triangle, but 7 and 8, that's just going to be a Pythagorean theorem to find what you need. So let's see, I don't even need that because remember the formula is 1/2 the two diagonals. Well, the two diagonals of number 7 are 4 and 10. 2 plus 2 is 4, 5 plus 5 is 10. So it'll be 1/2 of 4 times 10. So that one's pretty simple. Notice on number 8, though, we're missing the sides of one of the diagonals. Just use the Pythagorean theorem to figure out that last side. All right, so that'll do it. If you have any questions, as always, send me an email, and I'll see you next class.